All right, welcome everybody to this webinar of 3DI on integral 1D, 2D urban modeling with 3DI. Let me check. Yeah, let's go to the next screen. First of all, let's shortly introduce ourselves. My name is Jonas van Schrojenstein Lantman. I'm the product manager of Nederlands Schuurmans Technologies. And I'll be hosting this webinar. I have modeling experience, I think, over 10, 15 years in the field, and I'm now leveraging that in trying to create the modeling software that you are using right now. Rob, maybe you can shortly introduce yourself.
Yes, I am Rob van Zee. I'm a consultant in urban water management at Nederlands Schuurmans. I use 3DI almost daily for water-related questions, also a lot of questions related to sewage and climate adaptation. And I'm also doing 3DI training sessions. And today I'm going to talk about the 1D, 2D connections in 3DI.
All right, thank you very much. First of all, the webinar is being recorded. And we'll be sending a recording to the registrants, and it will also be published later on YouTube. The participants are anonymous, but if you ask questions, your name might not be anonymous. So please be aware of that. So the contents of the webinar, what are we going to talk about? First of all, I'm going to give you a very short introduction about 3DI in urban areas, and then Rob will give you a demo on building an integral urban model. So first of all, 3DI. What is 3DI? Well, 3DI, I'm going to keep it very short this webinar, is hydrodynamic simulations, interactive and online. It can be applied in various fields for flood risk management, urban planning, drainage design, integrated water management. So if you're looking at this webinar and you don't have a 3DI subscription yet and you would like to know more about it, you can go to our website, 3diwatermanagement.com, get a free trial or book a product demonstration if you would like to know more. So first of all, this webinar will be focusing on the urban areas, and I have some use cases just to show you, give you an idea of what 3DI is being used for. So this is an example, a holistic approach to the water system in the municipality of Assen, the Netherlands. And what is unique about it is that what we built here is a model where we did not cut the urban area in several pieces. No, we took the whole city as a whole, including the sewage system, including the outskirts, the rural areas, to have the inflow into the city as well. And by doing so, we have a good grasp of the actual flow in the urban system. Oh, wait, I have to use the mouse. Sorry. So, and another one, for example, is climate resilience on Centrum Island, Amsterdam, which is like a very relatively small model where we are looking into the impact of, for example, green roofs, like as an example of sustainable urban drainage solution on this area. Will that mitigate any potential impact of climate change? So these are just some very short introduction of use cases. There are many more use cases available on the website. So if you'd like to know more about them, feel free to go to the website and check them out. So 3DI in urban areas. How do we solve the models? Basically, we have three options. Well, there are more, but this is the three main options that are being used. First of all, there is the traditional urban water models, where you are looking at a traditional 1D solution with 0D inflow. You can also do a quick scan of a urban water analysis, which is basically you take a digital elevation model and you're going to look at overland flow and check where water might be accumulating. And you can do that without any sewage system included. This might work well if you have a peak event and you're not interested in what is going to happen afterwards. However, what you see that in reality, it's not always one peak event, but multiple peak events, and then the drainage of the sewer system is also going to play a part. And then you want to include both the sewer system and the overland flow in your simulations, and in some cases even the groundwater can play a part. So the traditional models, well, just to let you know that it is a possibility as well. There are, of course, many different software out there that have been doing this in the past. And with 3DI, it is also perfectly possible to do that as well, to have a 1D sewerage model, including any control structures that you like, and with 0D inflow from roofs and paved areas. So how does that work? The inflow from the roofs. So basically, if there's any water going on the roof, there is a very simple formula that is being used. You can, as a user, you can define the storage, you can define the evapotranspiration and the infiltration. And based on the precipitation, some netto precipitation runoff will be computed to the the inflow in the sewer system. Depending on the type of roof that you have, the storage or the infiltration parameters might change. And there are two options in 3DI. You can either use the impervious surfaces or the surfaces. The biggest difference is that with impervious surfaces, you have predefined types, and these parameters are predefined. And if you do surfaces, you can basically define any kind of parameter that you like. So this is how the inflow from the roofs work. But in reality, of course, the water is also flowing on the streets, and it's going to go into the sewer system. That we are doing using integral models, as we call them. We call them integral because we are taking the rain on grid, as it's called, the rainfall as it's coming on the actual elevation model, and then it can flow into the sewer system via 1D, 2D connections. So how does that work? What you can see here in this picture and also in the orange arrows, basically the water is going from the streets into the sewer system, and it does that on a certain exchange level that either the user defines or that 3DI takes from the pixels in the computational cell. So this is different than what happens in some other software where the inflow can be going directly into the sewer system itself. 3DI is basically always rain on grid by default. If you want to have the inflow differently, that is of course also possible. And the last thing I would like to address before we are going to the demo is the way that 3DI solves the equations, the way that 3DI basically solves the equation for the overland flow and the sewerage system. So traditionally, you would have some dynamic coupling where you have a 2D surface flow solver and you have a 1D flow solver, and they solve, like, for example, there is water going through the 1D system. It is going out of the 2D into the 2D, and then a certain amount of water is going to be exchanged between the 1D and the 2D, and these solvers have to basically talk with each other. Okay, I have so much water, I have so much water going in, so much water going out. And you can either have a very accurate estimate of the water that is being exchanged. If you want to do that, it means that you will have a very high time step iteration, meaning that your model is going to be slow, or you choose to have a less slower model, but then the exchange will be more inaccurate and it will be more of a sort of a guess. You can see this in the flow summary, in the so-called mass balance error. There's an estimate of the potential error that is being introduced in your models. With 3DI, this mass balance error is very low. It's actually one of the few, maybe the only one that is being in the flow summary in scientific numbers, because it is usually very, very small. And why is that? That is because we solve the surface flow and the 1D flow together in the same solver. So there's no separate solvers. It's just one solver all together. And that makes the exchange very stable and also faster than the traditional technique of basically exchanging water between solvers. So that also, with 3DI, we also introduced rainfall from real-world events. Of course, you don't have to use it. You don't always have rainfall radar data available in any area of the world, or you want to have some sort of design rain. That's also, of course, perfectly possible. And in some cases, you also want to maybe do a forecasting. And for that, we have also potentially hooked up to forecasting systems all over the world that you can use for a forecast. And the nice part about this, you can, from very complex, have rainfall that is changing over time, but also spatially different, to very uniform rain, constant all over your model. And it's up to you, to the modeler, to decide which one of these options to use. So this is a very short introduction of the 3DI in urban areas. And now I misclicked, I think. Sorry about that, Rob.
No problem.
So I'm giving the mouse to you.
Yes.
Please continue.
Thank you very much, Jonas, for this introduction. I'm going to follow up with some more in-depth explanations about the 1D, 2D couplings. What are they? How are you going to use them? And what are the important settings to look at? So first of all, we're going to use an integral model for this explanation. There I'm going to explain a few terms, like, for example, rain on grid and rain on buildings. Eventually, I'm going to talk about a little about overland flow, and that will eventually lead into inflow into the sewer system. And I'll also talk a little bit about flow through the sewage system, but that will all become more clear when we go into the actual 3DI model. First, I'm going to give a conceptual explanation about what actually are these couplings in 3DI. So therefore, you've got multiple options. I'm going to start with the first one, I think the most easy one. And that's when you have a 2D grid, which are all the blue lines, and 1D elements in your model. So when they are isolated, your 2D grid can have a different volume balance, different water levels than your 1D grid. And they are not coupled, so no exchange of water is happening between them. The second one is when they are connected, when there actually is a connection between the 2D and the 1D grid. So for example, there's a lot of water on the street and there's room in the sewage system, then water can flow from the street into the sewage system in this connected area. And they have two distinct volumes. And why is this important? Well, that's for the third option we have, and that is embedded. And in an embedded system, you still have your 2D grid, you have your 1D elements. Only what happens is that you say the volume of the 1D elements is the same volume as the volume of the 2D elements. So you also have the same water levels. And what actually happens is that you don't have two different calculation points anymore, but you only have one point where the water level is located. And this, you use it, for example, when you have very small 1D elements that you can't capture in your digital elevation model. And then you can embed very small elements and still have some hydrodynamic processes in your model. So far the conceptual idea of the 1D, 2D couplings. Now I'm going to do a quick demo about what they are and some more explanation about the settings and stuff. And also I'll show you some results. So therefore we go to 3DI. I already opened the modeler interface. And first of all, I'm going to load in map. So Jonas already showed you a map of Assen, a certain case study we did. And we're also going to the northern Netherlands, to Assen, but then a bit more east to the village of Loon, because that's where I've got a demo model of. So I already have the model here. I'll load this schematicization in. To take a few seconds. And then we're going to look at what's happening in the small village in Zurich. And we're also show you some things that are possible with stylings, which I use a lot. Okay, I'll put the map below. And we'll put the grid refinement off for now so we can see it a bit clearer. So here we've got the village of Loon. And you can see there is a lot of storm drains, which are the blue lines, and some combined sewage through here. And how this system works, what I do is I look at the cross sections of the model. So here you can see what are the cross sections in the model, and you can see the larger the cross sections become, the closer we're getting south. And that's mainly an indication that water flows from all over this area to the south. And here you can see there's a pump station in the combined sewage. So this is where all the combined sewage gets pumped out. And here you can see as well an outlet for the storm drain. And this is where the water flows out in the storm drain. So it's all going south. But you also can see there are some very big combined sewage pipes here. And the little bit smaller one go to the overflow over here. So when it's raining too much and the combined sewage can handle it, then water overflows here and then it gets transported over here. What I also can do, I can adjust the styling to levels and flow directions. Therefore I put the model rasters and the background map out, and you can see those little arrows, and that's actually the inclination of the sewage system. So this is also a way to see where the water is flowing. But what we're going to look at today is, put the rasters back on, this little string. And we're going to decouple it, because now the string is connected yet. But first of all, I'm going to a bit deeper into what's actually happening when you put rain on a model. So when it rains, water gets everywhere. It gets on the roofs, it gets on the roads, it gets on the grass fields. And we start with the roofs because they're kind of special in hydrodynamic modeling. How we implement roofs they are not in the 2D grid, but they are 0D surfaces. So what that means, we take a simplification of roofs and directly store the water somewhere. And that's what you see here. So here we've got a roof. And the water that is raining on the roof actually gets transported over these smaller lines. So it's getting split. So this roof is decoupled. Probably the front is going to the storm drain and the back is still going to the combined sewage. And here you can see in the impervious surface map, let's see, that 50% of this roof is going to this connection node. The connection node ID of this one is probably this ID. And 50% is going to this connection node. And what's happening then, if it's raining a lot, then water gets put into the sewage system directly. So when it rains on roofs, water flows over these impervious surface mapping and gets into the sewage system. So so that's a 0D, 1D coupling. But we're going to look at what's happening when you have 1D, 2D couplings. So when it rains on the grass, when it rains on the roads, where's the water going? Well, we have got a few connections between 1D and 2D in 3DI. And one of them are manholes. So these manholes are locations where water can flow from the 2D domain into the 1D domain and vice versa. So water can also flow from the 1D domain in the 2D domain. We've got a nice styling for that. So if we choose calculation type, check it out. Here you can see that all these manholes are put on isolated. So what's happening when it's raining a lot? Water cannot flow from the 2D domain into these manholes, but it can flow from the 2D domain to these manholes because these are connected. See? Yeah, and I can see that most of the system here is already decoupled. And I'm also going to show you that it's in the back of 3DI that's really happening like that. So I already looked it up here. We can compute a grid from this model. So here I'm going to show you the 3DI computational grid. We have a tool for that. Input spatial light. Here we've got the 1D, 2D connections. And I'm going to compute a grid from the spatial light, so from the schematization, and see what's, oh, I don't want it twice. Now I'm getting it twice. Not really a problem. I'm just going to throw one out. Put in top. Okay, so what we see here, the rasters out, background as well. Maybe this is easier. Okay, so here we've got our combined sewerage and we've got our storm drain sewerage. And these lines, the dotted lines, I can also style them a bit different. Let's see, single dotted line. We'll make them neon. So these are the 1D, 2D couplings we made. And here you can see this connected manhole is connected to the 2D grid, but this isolated manhole isn't, because here is no connection. And that's really important for this one, because what we can do is we can change, for example, this manhole into a connected manhole. So here I'm going to the settings of the manhole. I'll explain a bit more about this later. Put this one to connected. Save it. Save the spatial light. Saved. Then we're going to compute the grid again. Okay, I think this is the new one. Yes. So I'm going to put that above the old one. The same lines. Again, there's a black line. And now you can see there are two 1D, 2D couplings with this grid. And that's all because I changed the how do you call it? The calculation type of this manhole to connected. Okay, so now I've shown you what it actually means to the grids. Then I'm now going to tell you a bit about the settings you need, because there are different kinds of manholes that we use, and that you can see here in the default. So we've got manholes, inspection manholes, outlet, and pumping stations. And if you don't know what it is, we have unspecified. This one in the combined sewage is an inspection manhole, and that's most of the manholes, and the manholes be lying below the road. So in general, you have got an ID of this manhole, some codes and display names, so you can remember what it is. And here we've got the calculation type, which I already showed you. We've got 3 types: embedded, isolated, connected. I just changed this one from isolated to connected, so water can now flow into the combined sewerage. And there are a lot of other characteristics. Some are very important for 3D hydrodynamic part, and some are mainly for the numbers being there, because for example, the shape, the length and the width are very important in sewage management systems like Kicker, but they aren't very important for 3DI calculations. Which are important though are the bottom level and the drain level. The surface level is also something that is mainly important in the sewage management systems. The bottom level, of course, is how deep the manhole is, and how deeper it is, the more storage it can hold. The surface level is actually the top of the manhole, but for hydrodynamic modeling, it's mainly important. What's mainly important is the drain level. And the drain level is the level where the water or the 1D can interact with the 2D. I have a small figure of that to make it a bit more clear. And that's this one. So what you see here is this is our manhole. It's a vertical structure into the ground. The bottom level is quite logical. It's the lowest point. The surface level is the highest level. And we've got our drain level. And this is the level where water, the number you put where you want water to exchange. So if the drain level would have been above the lowest bottom level, for example here, then water can only exchange at this drain level. But what's happening now, the manhole drain level is laying below the lowest 2D bottom level, below the lowest pixel. And then 3DI is doing something smart. It doesn't actually look at, okay, what is the lowest drain level? What's the value of the drain level? But it's looking, okay, what's the lowest pixel? And then it makes a new sort of drain level, which we call exchange level. And this is actually the level where the 1D and the 2D connect. Now you maybe think, why is it important that we have the drain level below the surface level? Because why don't you just keep the drain level at the surface level? Well, normally manholes are put in the middle of the street. Maybe I can put a different background map to show you that. So for example here, let's quickly put the buildings off. So here you can see that the street laying here and the storm drain is laying in the middle of the street. But if you look at the model rasters, then you can also see that the middle of the street is a bit higher than the sides of the street. So I've got a profile tool. I can draw a little profile right here. Add this layer. And you can see that the sides of the road are 10 meters above NP. And the middle of the road is about 10 centimeters higher. So what will happen if you put your drain level at the same height as your surface level, then water can only flow in at this height, so at the middle of the road. But water that's at this height or at this height, so the sides of the road, can't enter the sewage. And normally when you have a sewage system, especially storm drain system, you also have locations at the side of the road, in Dutch it's kolken, where water can enter the storm drain. And therefore it's more realistic to have your drain level about 10 to 30 centimeters, 15 to 30 centimeters below your surface level. And that's why we do that. Then a few more characteristics of this manhole: visualizations, just how you want to show it. For example, you've got outlet and pump. I'll quickly go over these later. You can have groundwater exchange, not really important for this demo. And then you have got something, the connection node. And the connection node is actually a different table. it's where the manhole is connected on. And the connection nodes is where all the calculations are done for the hydrodynamic modeling. And what's really important about this one is the node storage area. I said earlier, 3DI doesn't use the width and the length of the manhole, which is kind of weird because normally, but manholes have a shape and that determines how much storage is at the manhole. And all that information is actually stored in this value. So the higher this value, the more storage is in your manhole. What's also important about this value is it's not only the amount of storage, but it's also the area that water can flow in or out this manhole. So when you have got a lot of water flowing over here, but you have, for example, a storage area which is very small, like this, then the water can only flow through this small area into your sewage system. So if you have a model and you have very small storage areas and the water doesn't go into your sewage, it is because of this value being very low. So if it's a very important point that a lot of water can flow in, you just make it higher. Just take into account that it can also influence the storage in your entire system. So that's about the main settings of an inspection manhole. And I'll go to pump stations, which are here. Pump station mainly have the same characteristics as a normal manhole. You have a manhole indicator. That's what gives it the nice look, as you can see here. And what's mainly important about the pumping station is that you have a large enough node storage area. So why is it very important? Water gets pumped out of a model at this location. But if you pump a lot of water out of a model, it should be able to also have that water at a location. So for example, if you put a value of 1 cubic meters here, and your manhole is 1 meter high, so if you total volume of 1 cubic meter, but your pumping station pumps 100 cubic meters a second, which is very large, then the pumping capacity is way larger than this storage area, and then you get instabilities in your model. And that's something you have to look at this location for pumps. Further, it's mainly the same as an inspection manhole. Then we go to outlets. Here you can see the outlet. This is actually the outlet of the entire system. And what's really important here is that the drain level is actually the same as the bottom level. So what I told earlier, in inspection manholes, it's mainly 15 centimeters or so below the surface level. But in the real world, an outlet very often isn't a manhole. It's just the end of a pipe. And therefore, we put the outlet level at the invert level of those pipes. Why is it actually a manhole? Why just can't you leave it just a pipe? That's because our manholes are connections between our 1D and our 2D domains. And therefore, an outlet is actually a location where water flows from your 1D, from your sewage, into your 2D, your creek, for example. And therefore, it's important to put there a manhole. And yeah, the reasons why you put it at your bottom level is because you don't want any storage in this manhole. It's mainly just has to flow out. Okay. I think I have told all the important aspects about manholes which I want to. I don't want to save anything. Manholes aren't the only things that can be connected or embedded. For example, pipes can also be connected or isolated. For sewage system, we mainly use manholes for that. There are also some other layers that can do that. For example, culverts can also be connected or isolated or even embedded. But what we're going to look at now, let's see. We're also going to look at some results because what's actually the effect of the things we did. I already loaded the results into my computer, because it's not the sake of the demo to also demonstrate how the simulation works. So here I've got, first explain a bit broader. In one version of the results, I have disconnected this entire sewage system, so the combined sewage system, from the 2D grid. So these are all unisolated, and in another version, all these lines are unconnected. So I'll load in the connected manuals, and I'll load in the isolated manuals, and then we're just going to look at some results. This is a bit smaller. Okay. Let's see, we have our two 1D, 2D connections. Here you can see again, let's put the compressors out. Let's put this one out. So here you've got the combined sewage and the storm drain sewage. And you can see, okay, it has a connection here and here. And what is interesting to know is how much water did actually flow over these lines. So what we can do, we can use the time series plotter. Make it a bit. Okay. And we can see, okay, this one was present in both simulations because we only decoupled this one. So if I put one of these out, I think this one. Yeah, so this one is only connected in this simulation. And in this simulation, there is the connection. So what we can see, for example, if we click on this connection, here we can see the difference over which the 2D, the amount of water that flows over this line. So when we decoupled the combined sewage, which is this simulation, you can actually see that there is about, I think it's 7 cubic meters extra going into the storm drain sewage, and which eventually will get transported all the way to this outlet. See? So that's one way to look at the results. What's also nice to see, another part of the results, is, for example, where does all the water come from? Okay, this button doesn't work right now, but we can use this one. So what we see here, we've got our storm drain sewage. And for example, I'm curious to know what are the water levels through the entire sewage. So here you can see at the start of the simulation, there's not a lot of water in the sewage, so it's a blue line. And over time, at this point, there's some rain in this middle. It rises, and in some locations, so for example here, water flows above the manholes, and then it comes on the streets. So what you see here, the brown, the gray area is actually the surface level. And then over time, it slowly drains again. And now the entire simulation is empty again. And there are a lot of more, and a lot of another analysis you can do in the simulations. We've got an entire toolbox for this. You can also make adjustments to the 2D grid. You can do adjustments in the 1D grid. You can model any type of suds. So for example, wadis or infiltration below the streets. But I think that's everything I wanted to show you about this model. I think I explained everything I wanted about the 1D, 2D connections. And then I'm looking at Jonas if he has anything to say.
Well, let's go back on the screen. Thank you very much, Rob. Maybe you can, well, I was going to say keep sharing, but
No.
because I have some questions. If you have any questions in the audience, feel free to ask any questions in the Q&A. There should be a tab available where you can ask questions, and I will come in. So first of all, you showed the roofs connected to the manholes, right?
Yeah.
You had these roofs, and they were all connected with these nice gray lines, and that's great.
Mm-hmm.
Do you have to do this all manually, or is there a tool available that can assist you in this?
Yeah, if you want to, you can do it manually, but that's quite a lot of work.
Exactly.
There is a tool available. And it's located in the 3DI toolbox. Let's see, it's in the 3DI schematicization editor, inflow, and there you have got a tool which is called Map Impervious Surface to the connection nodes. So how to map all the buildings to the sewage. And here you can fill in a lot of parameters which are important for your connections. You can even do a preference. So for example, if you want your stormwater to be close, those buildings close to this stormwater drain, you want them earlier to connect to the stormwater drain than to the combined sewage or the sanitary sewage.
Mm-hmm.
And when you click on run, it will connect all those things automatically. It will add it to the impervious surface map. And then you've coupled your buildings.
It will add it to the existing connections you already have.
Yeah.
So
yeah.
you have to be aware that you're not doing any double coupling, I guess.
Yeah, that's true.
Okay, so well, that's of course up to the modeler to keep in check. One thing I wanted to add, you were talking about the pipes that can be connected as well. Of course, the manholes we showed you have the manholes can be connected or embedded or isolated,
Mm-hmm.
and the pipes can be connected and isolated as well.
Mm-hmm.
One question that we sometimes get is from users that want to connect the gullies directly to the sewer system, and of course you can. Manually, you can add them to your schematization, and then you have basically, for example, orifices going from from the gully to the pipe, but that will add a lot of extra computational points, calculation points, and that might slow down your simulation. So when you use connected, you can change the distance calculation points. Maybe you can show that in the pipes. And if you change that to a lower number, then most likely you have something like 1,000 in it or something. I have no idea. Let me see. Oh, on top, yeah, you have distance between calculation point. It's now on 1,000. That means that on this pipe, for every 1,000 meters, an extra calculation point will be added. Well, this pipe is, I don't know, but nowhere near 1,000 meters. So if you want to have extra calculation points, with an exchange between the 1D and the 2D, you simply make this distance smaller, and then it will automatically be a 1D, 2D connection in 3DI.
Can you even show it? So now we made this line connected, save it to Spatialite. And then we're going to regenerate a grid again. And then you can see a lot of extra connections will be made from the pipes to the 2D grid. So here we go again.
Yeah. Well, it's good to add that what you're doing here is all local on your laptop. So you're basically using the same tool that is being used on the server. The actual computational grid, or the computational grid that 3DI will use in the calculations, will be generated on the server. If you have your plugins up to date, then you will have exactly the same grid as on the server. But if you have very outdated plugins and we have updated something to the software, then potentially, theoretically, your computational grid might be different than that is on the servers than with 3DI is being used. You will know because the moment you download your results, as Rob showed, you will see the computational grid that was used in the calculations. So you will always know the computational grid that was used in your calculations. There are no surprises there. And everything that is being used by 3DI can be found back in this computational grid. So there's no hidden results in that sense. You gave quite some pointers about the storage areas, and you said, okay, this has to be larger, and with the pumps, it has to be larger. Maybe you can show where the tool is for the schematization checker. Of course, there is a checker the moment you upload it, your schematization to the server. You can say, okay, do you want to check my schematization? And then you check it. And then you get a lot of feedback potentially you get a lot of feedback. Hopefully you get nothing, but there's usually something that is being added in the feedback. You can also just run the tool locally, and then you get like a table in your table of contents for everything that is, and it's of course tricky to do this for this demo. There might be, we didn't prepare this, so well, let's see what comes out of it. What you get back is, I don't expect any errors, because an error would mean that the model cannot be generated, no simulations can be run. This can, for example, be when there is no profile available for a channel, or you somehow manage to not have a diameter for a pipe, for example. This kind of thing you cannot run a simulation on. But if you have, for example, warnings or info messages, then, for example, it adds it somewhere in the...
Yeah, I clicked the wrong one.
Okay.
Yes, check schematization. That's the one.
Oh, okay. Sorry, I was not looking at what tool you were running.
No, me neither.
Okay. So, luckily the tools are very fast. So if you can open it.
It is opened. Oh, you can see that. Oh.
We cannot see that.
Wait.
Somehow. Not sure why.
I didn't share my screen, but I should.
Oh, you shared the window. Yeah, okay. Yeah, that makes sense.
Again. There aren't any schematization errors.
There's nothing. Okay.
Nothing. We built a very good model.
Okay, well, for the demo purposes, it would be nice to add a mistake, but you get, for example, if you make the storage area for the pump station, can you make that one very small?
Yeah.
And then run the check again? Because there are these kind of things you can check as a modeler, and of course, this is a simple model, and you do one check and you're done. But if it's like a larger area, for example, the one of the whole municipality, there are, I don't know how many pumps. To be honest, I don't know, maybe 20, maybe 30, maybe 50. But if you have to check them all manually, that can be cumbersome and potentially also not necessary. So you will get warnings for that. And you get a warning because that means you can run the simulation. There is no problem with coming to a solution. However, if you do so and your simulation is slow, or the results are not as you expected, the first thing we always advise is look at your warnings and adjust the warnings to make sure that there are no warnings at all anymore. And that will make your schematization, your model simulation most likely quicker. And also you will have no unexpected results. So the unexpected results can mainly happen in the case of this pump station capacity thing. That's why we emphasize it. This is for hydrodynamic simulations, never a good thing. I'm not sure how many checks we are doing at the moment, but it's either hundreds or 1,000 or something. So it's a no regret to run this check schematization thing and solve your warnings for sure. The info you can read and take as information. If you don't understand any of these warnings, any of these infos that you get back, or the errors, feel free to send an email to our service desk @nelischumans.nl, and ask the question, and they'll be happy to help you with that. I have one more question. Can you show a weir? Do we have a weir in the schematization?
We do have a weir.
Okay.
So this is a location where the combined sewage system overflows when there's just too much water.
Perfect.
Entering.
Can you maybe just click on the attributes and explain a little bit about it?
About this weir?
Yeah, just what, I mean, it's just for those in the audience that have never seen it in 3DI, I mean.
Okay, well, normally when you look at a weir in real life, it's not a very long structure, I think most of you think. But in 3DI, it is modeled as a line. So it's a line between two manholes. And why is that? That's because you need to have different water levels in front and at the back of the weir to have a scientific formulation for it. Yeah, in 3DI here we have it, and these are the attributes that are coming with it. Most important attributes of a weir are the crest level, so that's actually the height of the weir. You can have a long crested weir or a short crested weir, broad crested weir, excuse me, and that's just a way of calculating it. If you want to know more about that, there's a lot of information about it on the documentation. I'll briefly show that. Docs at 3DI Live. Where 1D objects where, and here you've got a lot of information about actually the rest of the wheres table. If I'm correct, also somewhere there's information about the crest type.
Right, yeah, here. Well, in the sewage system in the city, you barely ever use broad crested, so you will almost always have short crested.
Exactly. Then there are some few more values. You have a discharge coefficient. This is actually a way of saying, okay, water can flow one way and water can flow the other way, and the easiness it flows. So if you have a very large coefficient, then the water can flow very easily. But you, for example, put it to 0, then water can flow back. And that's very often in the case when you have a clap. You know what it is?
A valve.
A valve.
Yeah.
So then one water can only flow one way. Then we've got the cross-section definition. And there are, of course, a lot of possible shapes of weirs as well. And here we use tabulated trapezium, and that's actually a nice way to have a lot of options to make your weir. So you can give it a lot of shapes. You can also just choose an open rectangle. Then it's just a rectangular shape which goes as high as you want it to. Closed rectangle, then it's actually a closed shape on the top. Circle, an egg. You can go all wild with the YZ profiles. So there are a lot of different options. Anything you want to add to?
No, yeah, just so this means that this is basically you have a weir, that's the crest level, and then on top you have some sort of like either space or no space. And with this you can sort of like take the whole, well, as Rob mentioned, the whole, how do you say that? The shape of the weir, if it's any weird kind of shape, but also the space available on top of the weir you can take into account. And this can be a thing in the sewage system, of course, where there might not be any unlimited free flow up till the sky. Well, I would like to, if there are no more questions coming in, I would like to round it up, and then I would like to thank you all for your attention. Oh wait, there is one question coming in, last one. Okay, the question is about the storage in the manholes. How can we calibrate those values? As you mentioned, if we put low values, the water will flow no easily inside the sewer system. If we put high values, then the water can flow very easily. Some programs like Swim have gutter equations to simulate how much water is coming from the 2D inside the sewer system. So, well, my advice would be to choose always realistic storage areas for your manholes. The equations that 3DI is using, I don't have the slide ready to be honest, but is that the inflow in the manhole is dependent indeed on the area of the manhole. So that will decide how much water is going in. So adding, if you have a very large area, it might get to unrealistic inflow in the sewer system in the gully. But this is something. So we do have these equations as well, basically. And I don't. To be honest, I think the calibration of your model will be more, especially if you have 1D, 2D, yeah, I'm not talking about 0D, 1D, will be more towards infiltration values and friction values on overland flow will have a higher impact on how much water is standing on the streets. Also, if you are going to validate or calibrate the actual rainfall amount being used is of high impact, especially if it's a larger area and the rainfall is spatially different, then this will have a very large impact on your modeling results and also on your validation and calibration. Imagine you are putting your time and effort in building the best schematization you can ever imagine. And if you then don't use the right amount of water going in, then those efforts are sort of like in vain. You have to sort of be in balance when you do that. You have to also make sure that the amount of water that you're going to put into your in your system is in line with the amount of effort that you put into building your schematization. And this is why with 3DI we support the option of also adding real rainfall radar events. I hope this answers your question. If you have a follow-up or you would like to discuss it more in detail, feel free to reach out to me and I'll be happy to have a more in-depth discussion about this. Well, we are also approaching 11 o'clock. So with that, I would like to thank you all for your attention. Also, if any other questions pop up later after listening to this webinar, feel free to email them to us and we'll be happy to answer them. If you have any suggestions for webinar topics, also feel free to email them to us. We have, of course, a range of webinars that we are going to give, but it's always nice to hear from the audience what I would like to hear. And I think from the top of my head, in 3 weeks, we will also, the first coming webinar is about 3DI water quality, in which we will show you the new or the relatively new option of water quality in 3DI, how it works, how you can apply it, and what kind of application areas there are for that. So if you haven't done so, subscribe for that webinar. It will always be recorded. If you can't make it live, we will send the recording later afterwards to you, and we will do the same with the recording of this webinar for those that were not able to attend. So that's it. Thank you very much. Also, thank you, Rob.
Yes.
Little clap from the audience, which you cannot hear. And thank you. Bye-bye.
Bye. Thanks for listening.